Hey, good afternoon, everyone. Welcome to the CS Colloquium. Today, we have the great pleasure of having Sasha Golovnev as our speaker. He's an assistant professor at Georgetown University. Prior to that, he was a Rabin postdoctoral fellow at Harvard University, a postdoctoral fellow at Columbia University, and a research scientist at Yahoo Research. He received his PhD from Courant Institute of Mathematical Sciences at New York University, and today he's going to talk about data structures, meaning circuits, and cryptography. Sasha, over to you.
Thank you for the introduction. Thank you everyone for coming. So today I would like to talk about connections between certain sub areas of theoretical computer science. So we'll see some connections between data structures, circuit complexity, and cryptography. Okay, so this line of research is motivated by the following question: what resources are required to solve a computational problem? As an example, for example, the classical prevalence-Salesman problem, where given a graph on n vertices, we want to check if there is a path that visits every vertex exactly once. We know how to solve this problem in time. For 60 years, we couldn't come up with a better algorithm, and several conjectures actually in computational complexity imply that this problem requires exponential time. So this is an example of a problem that might actually require exponential time to solve. Even if we just prove a super polynomial, not exponential, but super polynomial power 1 for this problem would resolve the biggest question in complexity. We would prove that p is not equal to. But there are similar questions, similar problems even within polynomial time. Say the edit distance problem where given two strings, I need to find the minimum number of elementary string operations that would turn the first string into the second. We know how to solve this. There is a textbook algorithm that solves this problem in quadratic time. We don't know how to solve it faster, nor do we know how to prove the n-square results. So there are many questions about computational or running time of algorithms for problems in exponential time, polynomial time, or super polynomial time. And yet, this is only one side of hardness, one side of computational hardness of a problem. So here we saw examples of time complexity of a problem, but we also might want to optimize other computational resources. For example, nowadays, in the era of data science algorithms, big data algorithms, we often want to understand the space complexity of a problem, because it's often the case nowadays that our algorithm cannot even store the input. So another resource we might want to optimize is the space. Or sometimes for certain learning problems, we want to optimize data, the number of correctly or well-labeled data points. We might want to minimize the amount of randomness, or want to understand what quality of randomness we need to perform certain cryptographic tasks. And in general, the area of algorithms or circuit complexity studies time complexity of the problem. The areas of, say, streaming algorithms or data structures are trying to understand space complexity of the problem. Learning theory is responsible for the amount of data, while cryptography, among other things, studies the amount and the quality of randomness we need to perform a certain task. Yeah, I forgot to say, please do ask questions during the talk. And recently we've seen a bunch of examples connecting these areas, and this is the purpose of the talk. In this talk, I'll show a couple of recent examples where we connect data structures to circuits and to cryptography. So the outline of this talk is the following. First, we'll see what we mean by data structures. We'll define the class of data structures we'll be discussing in this talk. In the second part of the talk, we will see that the main question in data structures, proving data structure lower bounds, is actually exactly equivalent to a certain kind of cryptography. Cryptography exists if and only if we can prove data structure lower bounds. We can prove data structure lower bounds if and only this cryptography exists. And this connection is actually proved. We will use a crypto trick that hackers used to use in the 80s to break passwords. We'll use it to refute a conjecture in computational journey. And in the last third part of the talk, we'll see connections between circuit lower bounds and data structure lower bounds. In fact, we'll see that the main question in circuits and the main question in data structure that we've been studying for 50 years is apparently the same question. And all our lower bounds exactly match for data structures and circuits exactly match each other. Apparently, we've been doing the same thing in two different communities for a long time. Okay, this is the outline of the talk. Please let me know if there are any questions. If not, then we'll start with the definition of data structures. Okay, so data structures. We all know a bunch of classical data structures: stacks, lists, heaps, all kinds of search trees, hash tables, blank filters, and so on. But in this talk, we'll be looking at static data structure. Let me give you a couple of examples of static data structure problems. For example, in the Google Maps problem, I'm giving you all roads of Singapore, and I want you to preprocess them. Like you are, say, a software engineer in Google, somewhere in California, have essentially unlimited computational resources and time to build Google Maps app. But once it's done, once I have the app on my phone, I want you to quickly answer the queries. What's the shortest path from me to a library? So you have essentially unlimited computational power to preprocess the data, all roads. But once I'm giving you a query, the shortest route from here to a library, I want to see the answer really soon. That's why it's called static. The input, all the roads of Singapore, are essentially static. We have unlimited time to preprocess it. But then the query faces a issue. In the Google Maps graph distance problem, you preprocess the roads and then give me shortest path to between different locations. In the nearest neighbors problems, I'm giving you a bunch of cluster centers. I can spend a lot of time to preprocess them, but once you're done, I'm giving you a query to find the closest cluster center. That's how many recommendation systems work. Another classical example is the range counting problem. Say I'm giving you a bunch of points in the game that plane. Again, you have a lot of time to preprocess them. Once you're done, my query is a rectangle. Count the number of points in the rectangle. Okay, all of these problems are static data structure problems because the input, the clusters here, the rows in the first problem, the points in the plane in this problem, they're static. They're never going to change. Okay. So pictorially, it looks as follows. This is input. Your preprocessing is computationally unbounded. You create some data structure. Once you're done, I'm giving you queries. What's the shortest path from one city to another? And I want you to look just at a few positions in the data structure and perform some live computations and give me the correct answer. Then I'm giving you another query. Again, you look only at a few positions and quickly find the right answer. So formally, static data structure is the following thing. You have n inputs from your favorite, say, field. Your preprocessing stage is computationally unbounded. You create a data structure, some S memory cells from the same field. And then I want you to answer each of the possible m queries efficiently. You're looking only at a few positions in the data structure. Okay, you know all possible queries, all possible m queries in advance. You know all possible pairs of seeds you can I can ask about, right? So you know all possible queries in advance. There are m of them, and typically we think of m as a huge polynomial in the input size in n. M can be n squared or n to the 100 or something like that. So n, the universe of queries, is polynomial in n, but usually like very large. Yeah.
Is there any restriction on S on like the size of your data structure?
Yeah, so what does it mean to design a data structure? That means I have a problem and I want to come up with a good data structure. So I want to simultaneously optimize the two important parameters, S and T. I want a data structure with small space and efficient T query time. Yeah, I want to simultaneously optimize two parameters. And typically I would say data structure is efficient if its space is close to optimal, like overhead or the input is small, so space is maybe n to the log n, and your query time is small, maybe 4 log n or n to the epsilon for some very small epsilon. Okay, that's the data structures we like, efficient data structures. Okay, so that's the problem statement. Every data structure problem admits two trivial solutions. The first one here would be In the computationally bounded preprocessing stage, we compute all answers. You know all M queries, just compute the answers to each query. Then your query time is ideal. You don't need to compute anything. You already have the answer. Just read it and give it to me. But clearly use a lot of space, right? This your S is prohibitively large. And the possible number of queries can be like n to the 100. Another trivial solution that works for every static data structure problem is the following. You just don't do any preprocessing, just store the input. Your space is ideal, just n. But for every non-trivial problem where query depends on all of the input, your query time must be linear. So we have two trivial solutions for all data structure problems. One of them uses has very large S, another one has very large T. And here, like in the field of data structure, static data structures, we're trying to understand what problems admit solutions in between of these two, where S is not trivial and T is not trivial, and T is not trivial. S is less than M and T is less than M. Is right.
So the M and N can still be polynomials.
Say that again?
The M and N can still be polynomials.
In what?
I mean, polynomial or something.
N?
Polynomial.
Okay, so we usually say they all are functions of N, and N is typically polynomial in N. But we don't want such a large space. We don't usually want like space to be n to the 100.
Sure. So just from a practical perspective, but from a theoretical perspective,
Even from theoretical perspective, we usually want S to be linear or quasi-linear in N.
couldn't there be problems that are harder than N, even if I have like the time complexity?
Okay, so there are two ways to measure time complexity. One is really how much time do you spend. Yes, there might be problems that require a time which is exponential in N, or depending on your computational model, maybe even undecided. Yeah, another way we usually use in this framework is how many memory cells you read.
Okay.
And let's, for the purpose of this talk, let's say T is the number of memory cells to read. We'll actually achieve the best of two worlds. Whenever we give lower bound, we say you have to read many memory cells. So your running time is definitely large. Whenever we'll be given upper bound, we'll say that our procedure will be as efficient as T. We'll run in time a linear and C. So we'll give upper bound on both the number of cells you're reading and the actual running time. Other questions? Good. So there are two trivial solutions, very large S, very large T. And in the field of data structures, we're trying to understand what problems admit solutions with smaller S and smaller T. Unfortunately, most problems or a random problem doesn't have no trivial solution. For most problems, for random data structure problem, once your space is less than n, you're immediately in this region. You have to use time linear in n. But the challenge here is always to find an explicit problem which is hard. Explicit here means, for example, one of the problems from the previous slide, Google Maps or Netflix or Amazon, something that we really use in real life. The formal definition here is find a problem from a reasonable complexity class, maybe P or NP or even E to the NP, from some complexity class that we have some understanding of, find a problem which is hard. So even though most of the problems are hard, we have no idea what they look like. Give me some description of a hard problem. For example, give me a problem from the class P, which is hard for data structure. And here, the best known concrete lower bound, the best known lower bound for a concrete problem from the class P, we can prove, was proven in the 80s by Siegel. It has the following form. Let me parse it for you. When space is linear, we can prove lower bound on time log n. Even though we know that a random problem would require time linear in n. So that's a very weak lower bound. And once space is superlinear, we can prove nothing at all. We can only prove that query time is constant, but clearly it's constant. You have to do it with sum. So that's the state of the art in data structure lower bounds. Any improvement of this bound would be a big deal. We can't improve on it in like 30 or something years. And yet, yeah, this lower bound is pretty weak.
What is the function?
Oh, that works for every function whose outputs are sufficiently independent. For example, for every like k-wise independent function for a large enough k, for every linear code. So you can think of this problem as polynomial variation, where the inputs are coefficients of polynomial and the queries are variation of this polynomial at different points. Other questions?
Sorry,
Yeah.
is there some notion of completeness in this class? Like, are there complete problems that everything reduces to? I mean, how does the proof go? Like, how can you say this for all data structures?
How can I say that no data structure can solve it with smaller t, or what do you mean?
I mean, there must be problems which are easier to solve than this.
Right, right. I'm not saying every problem requires this data structures. No, I have an explicit problem
Right.
that requires large data structure.
Okay. And how do we? I mean, what's the nature of the proof for this? Like, you just need to find, let's say, the polynomial problem and show that this is hard.
Right, right. What's the nature of the proof? How do I show it? It's an information theory argument. And saying if you get a smaller data structure,
Right.
Here's a contradiction you will get. Yeah.
Okay. Okay. And that's okay. Understood.
Other questions? All right. So okay, this is the state of the art in static data structure lower bounds. Now we're moving to the second part of the talk, cryptography with preprocessing. We'll prove that a certain kind of cryptography with preprocessing is exactly equivalent to proving data structure lower bounds. All right. So for cryptography, we need one-way functions. We need functions that are easy to compute but hard to invert. Cryptography just doesn't really, like, interesting cryptography doesn't even exist without such functions. Okay, but it's just the rule of thumb that you don't design such a function yourself. If you found a function that you think is hard to invert, then most likely your neighbor would actually eventually invert it. So what we do in real life, we find a function, we test it, then we publish it, then the cryptographic community tries to break it for 10 years or so. And if they didn't find any problem with this one function, then we eventually start using this function. So it's a long process to make sure that no one really knows how to invert your function. And the problem with this is that say you found such a function some 30 years ago, standardized, published it, everyone tested it, but back then probably you wanted to have this n like reasonably small so that you could efficiently compute the function. Nowadays, when we have fast computers with a lot of space, I could break such a function if I had enough preprocessing. Like the trivial way would be just if nowadays my new big computer is so big that I can store 2 to the n numbers in it, I would just store 3 images of all of them in my new big computer, which we couldn't do back like 40 years ago. And now I could easily invert a function at every point. But that's a trivial example. There is a whole class of attacks called rainbow table attacks that don't require you to store that much space. So the point is that nowadays, since we have like much bigger computers which are much faster, we can actually break some of those functions with preprocessing. That is, we look at the function that we published 40 years ago, preprocess it, and after this we can efficiently invert. Yes.
Sorry, very naive question. Why n is the same in the domain and the image?
Not necessarily, just for simplicity, just for the definition. It's sufficient for cryptography. It's good enough. In general, you don't have to define it this way. If you have a hard function from n bits to n bits, you can actually construct hard functions from n to 10 n bits as well. Yeah.
All right.
Just for simplicity, here I define it this way.
One way function is still conjectural.
Sorry?
One way function is still conjectural.
Yeah. We don't know if they really exist. If they exist, then for example, p is not equal to p. We are really far from proving that they exist, but there are many candidates. We believe that many functions are hard to invert. Yeah. Other questions? Okay, so what do? Some 40 years we found the function, n back then was small. Nowadays it's not a secure function because we have preprocessing attacks on it. So one way to resolve this issue would be to design a new function with much larger n, publish it, test it, wait until everyone tries to break it. It will take some 10 years, and then start using it. So that's a long process. Instead, we would like to reuse the old function in a way which is secure even against modern computers. So ideally, I would like to take this function, based on it, design a new function probably with much larger input and output, so that to design attack is not very helpful there, which is still secure. If I believe that the old function was secure, we would like such an immunization procedure. And in fact, in a recent work, we proved that such a procedure is possible if and only if one can prove data structural bounds. We can take an old, not secure anymore function and turn it into a new function which is secure even against modern big computers, if and only if we can prove data structural bounds against a certain class of problems, but this is a huge and natural class of problems. It includes 3 some nearest neighbors, polygon containment, almost all computational geometry here. I don't want to formally define this class of problems. Instead, I will show you one problem from this class, and I will show you what else we can get from this connection between cryptography and data structure. So let me define you this 3 sum problem. We'll be working with a data structure version of 3-sum problem, but let me first remind you what the classical algorithmic version of the 3-sum problem is. There are given n numbers, say integers. We want to check if 3 of them satisfy the following equation: ai plus aj equals a. Even though it looks like a problem about numbers or maybe combinatorics, is actually the foundation of computational geometry. If this problem is easy, then like many problems in computational geometry are easy. If this problem is hard, then they all are hard. And there is a textbook algorithm that solves this problem in quadratic time. And in fact, some 27 years ago, it was conjectured that this problem requires quadratic time. We could show off a couple of log factors. We could solve this. We eventually solve. It's stuck. It doesn't seem. I can see. Changes on the screen.
usually make sure that something. We are battery gone.
No, I can see the change on my screen. Okay, so eventually we set a couple of log factors. Oh, I understand. That was it.
It's a one-way function.
Yeah.
Basically, if you take one function, start and end it, if you go through the process, and you expand that, which probably same you had lower down data structures.
Not sure about
Technical, I'm not
chat are slightly confused with what's going on. Maybe we should not reply. I think people are slightly confused with what's going on.
Yeah, sorry about this. Let me remind you what we know. So we figured there is an equivalence between cryptography with preprocessing and data structural lower bounds for certain class of problems. One of them is a three-sum problem. And so now we're just recalling what the algorithmic version of the three-sum problem is, and then we'll see the data structure version of this problem and its connections to cryptography. Okay, in the algorithmic version, given the numbers, we want to figure out if three of them are roughly 0. There was a conjecture saying that probably you cannot solve it faster than n squared. We did solve it a bit faster, but still the modern three-sum conjecture says that maybe you can save a couple of Golovnev factors, but you cannot solve it in truly subquadratic time, in time say n to the 1.9 time. That's a modern three-sum conjecture. We don't know how to prove it. We don't know how to refute it. Any of this would have major consequences about computational complexity of like a whole bunch of problems in our.
It's still active.
Yeah. Okay, so that's the classical algorithmic version of three-sum. Here's data structure version of three-sum and the corresponding conjecture. Here, I'm giving you n numbers. Let's preprocess them into s numbers, such that given a query B, you can answer in time C this query. And what does it mean to answer the query? I just want to check if B is a pairwise sum of E. Okay. So again, that's the data structure version. So here we have S and C, space and time. And it's again easy to solve with quadratic space and logarithmic time. How do we do this? We just pre-compute answers to all queries. That is, we just store all pairwise sums, maybe sort them, and then with some binary search, I'll always find an answer with some say logarithmic time. And on the other hand, I can just store sorted input, and then using this two-finger algorithm, I will always in linear time find an answer to a query as well. So I can store it with quadratic space, which seems too high here. I can store it with linear time, which is again like trivial time. And there was a conjecture saying that there is nothing in between. Once you use less than quadratic space, you're immediately in this region. You have to use linear time. So now that we know that this problem is equivalent to cryptography, we'll actually use the crypto trick to refute this conjecture. We'll now construct a data structure with truly subquadratic space and truly sublinear time. Okay. For this, we'll use a primitive from cryptography called function inversion. Okay, so here's what it is. Say we have a function from integers from 1 to n, capital N, to integers from 1 to capital N. And we want to preprocess it, store s numbers. And now, given I want to be able to answer queries in time t. What is a query? You give me some y, and I return x such that f of x is y. I want to invert function f and function y. Okay, given function, preprocess it, and I'll quickly invert it at any time. And Hellman and Knauer gave a surprising algorithm for this problem. For example, they said that for every function, you can always invert it at every point in space and time, and to the three coordinates. Let me show you because our algorithm works in the special case when our function is bijection. That is, it maps n numbers to n distinct numbers. Okay, we'll do this in say square root of n space and time. So we have a bijection from n to n. We want to invert it in space square root of n and time square root of n. How do we do this? We first define a directed graph whose vertices are numbers from 1 to n. Now we draw an edge from x to f of x for every x. So every vertex has exactly one outgoing edge. And since f is bijection, it has exactly one incoming edge as well. So this is a directed graph where all degrees are 1. What does such a graph look like? Just a bunch of directed cycles, just a union of cycles. So in the preprocessing stage, I draw all of the cycles. And now let me zoom in into one of the cycles. I pick any vertex here and I say this is my landmark. Then I skip the next square root of n vertices and I say this is my next landmark. I skip another square root of n vertices, mark the next vertex as a landmark, and so on. All what I do in my data structure is I store all the landmarks, and for each of them, I also store a link to the previous landmark, which is square root of n vertices apart. Okay, that's all of my data structure, and clearly the space I use is at most square root of n. Why is it so? I store a number and I skip the next square root of n number. Okay, so it remains to show that whatever query you give me in times square root of n, I can actually invert it. That is, you give me some y equals f of x, I want to find x. Y is some vertex in my graph, and recall how I constructed the graph. There was an edge from x to f of x. So x is just the previous vertex in the cycle. Given y, I want to find the previous vertex in the cycle. So how do I do this? I start at y, apply function f. So I just move along this edge. I apply function f one more time. I move along this edge. Once I reach a landmark, I can jump to the previous landmark and keep going until I see x. My query time is upper bounded by the length of this arc, right, which is square root of n. So I inverted this function in times square root of n. Okay, so now using this Greek, we're going to solve a data structure version of C-sum. In the data structure version of C-sum, we're given a numbers, given a query, we want to check if this query is pairwise sum of the input. So let me first define the following silly function. It takes two indices of the input numbers I and j, and just outputs ai plus aj. Let's note a couple of properties of this function. So first of all, f is very easy to compute, right? Given two indices, you just sum up a couple of numbers, that's it. Second, what's the size of the domain of this function? I is the number from 1 to n, j is the number from 1 to n, so the domain is of size n squared. And since the output of this function is always a pairwise sum, one of the n square sums of the pairs of these numbers, by standard Hessian tricks, I can always hash down the output of the function to integers from 1 to say 10n squared. There are only n squared possibilities. I can always hash them down to numbers from 1 to like the order of n squared. So without loss of generalities after some Hessian, I can assume that the range and the domain of this function are essentially n squared. And now the final property of this function is if you invert it, you solve 3-sum, because 3-sum is exactly given a number, other indices I and j, such that ai plus aj is b. So it's sufficient to invert f to solve the data structure version of 3-sum. I just want to use this algorithm by Hellman and Piatnor that inverts any function in non-trivial time and space. What do I need for this algorithm to work? I need f to be easy to compute, which I have, because remember, while walking along this arc of a cycle, I keep erasing f. So I want f to be easy to compute, but I have it. I need small domain and range because that's the main capital N parameter function inversion. It's reasonably small. So Hellman and Piatnor give me an algorithm that inverts a function and that solves 3-sum in any space and time ST that satisfies certain equation. In particular, I can pick really truly subquadratic space and truly sublinear time. Yes.
The algorithm you just gave on the previous slide, is that not required to be a bijection? And
yeah, this algorithm is a special case of Piatnor algorithm that works only for bijection.
Yeah.
And it achieves amazing, in fact, optimal parameters. S and T can be as low as square root of n. For general functions, I didn't present the algorithm, but Hellman and Piatnor did. their algorithm is slightly worse. The parameters are slightly worse, but they're still good enough for our application.
Okay, so they've generalized it
Yeah,
with
yeah.
The question is only probabilistic, right?
The question trick is probabilistic in theory, but if you want your data structure to be deterministic, you can do this because you have unbounded preprocessing power. So in the preprocessing stage, you can like brute force all hash functions and find one that works for you. Then you get rid of any probability. So if you're fine with computationally unbounded preprocessing stage, you can get rid of the probabilistic part of the stage.
Can you do any better if the inputs are random?
You can do better if inputs are random because Hellman and Kratnauer give a better algorithm for for a random function. Yes. It would be essentially s squared times t equals n equal.
It's assuming unbounded pre-processing time reserve.
Assuming unbounded preprocessing time, yes. But
That's reasonable.
that's the definition of this model. Not
Yes, I
clear.
know it's better than model. I'm just asking. Reasonable.
I guess so because how do you bound the computational power Google has when they design Google Maps? I mean, it's essentially unbounded.
No, not true.
Luckily, if you allow our data structures to be randomized, our preprocessing and query phrases are extremely efficient. They're linear and inputs. All right, any more questions? Okay, so that's an example of connection between data structures and cryptography, but in general, we prove that cryptography with preprocessing exists if and only if certain data structure problems are hard. All right, and in general, how could we you remember this question we started with? We have an old function which is secure, but the n is small. So it used to be secure, not secure against the modern computers, and say 3 sum is hard. Then I can design a new function which is secure even against modern computers. And in fact, this design, this implementation procedure is just like the pipelines of code. All what you do is you first increase the range of the function almost in any way. For example, you can just say that my new f prime is just a combination of 2 outputs of the of f. And I will say my new hard function, which is secure even against stronger computers, is just sum of two variations of the old function. That's it. That's like 3 lines of code, and you get a new function which is secure against stronger computers if the old function was secure against old. Yeah.
Sorry, what does it mean to apply f to 2 arguments? Takes 1.
Yeah, that means that the first bit is 0, the next n minus 1 bits are x. The original f took n bits as in. Okay, more questions? Good. So if we could prove that some problem says 3, some nearest neighbors is hard, then we would have cryptography with preprocessing. So in this work, we actually prove some lower bound for 3 sum, and it actually matches the best known lower bounds we could prove for any data structure problem, but yet it's not sufficient for cryptography. For cryptography, we would need to prove much stronger data structure lower bounds. But apparently, there is a barrier. If you prove stronger data structure lower bounds, then you resolve another open question in circuit complexity. And this brings us to our next work, which connects circuit complexity to data structures. Any questions about this part? We're about to start the last part where we see that data structure lower bounds are exactly equivalent to circuit lower bounds. All right. So in circuit complexity, we want to compute functions, say Boolean functions from n bits to n bits, and we compute them by so-called straight line programs. So programs where you don't have any branches. You don't have if statements, you don't have for statements, you just run it line by line. Okay, and such a problem can always be represented as a directed acyclic graph, which is called a circle. So you have n inputs, you can use Boolean constants if you want 0 and 1, and every gate just computes some Boolean operation of two previously computed things. Okay, and the circuit size is a number of gates in such a circuit. We do not pose any restrictions on our degree of gates or on the depth of the gates, or just consider circuits. Okay, and in the 40s, Shannon showed that actually most functions require circuits of size 2 to the n. And like in 50s, Lupanov showed that actually every function can be computed by a circuit of size 2 to the n. So most functions are exactly 2 to the n hard. We have exponential complexity, but as always, the challenge is to find an explicit function which is hard. Say a function from the class NP. If we find a function from the class NP which requires not even exponential but just super polynomial size circuits, we would already resolve the P versus NP question. And the best what we can prove is roughly a lower bound of sphere. Even if we consider problems from a much larger class, exponential time with a computer that can solve and hard problems of exponential length. So even in a much larger complexity class, we don't know how to prove strong allowable bounds. So we know almost all functions have exponential complexity. We just need super polynomial complexity. The best we can prove is essentially the n.
So when we say most functions,
yeah, I mean,
what class are we referring to?
Yeah, you can define the class of functions from n bits to n.
All possible functions.
Yeah, there are 2 to the n functions. 1 minus little of one fraction of them has complexity exactly 2 to the n. And that's the best we can. Okay, so the first challenge here is okay, maybe you can prove at least superlinear circuit law. This challenge was posed by William essentially 50 years ago. We still can't prove it, but we have many candidates for superlinear circuit law. For example, recently we learned that 2 n-bit integers can be multiplied by a circuit of size n log n, and people tend to believe that this is optimal. That maybe this is one of the functions for which we could prove n log n circuit law. We'll say discrete Fourier transform. We know how to do it in time n log n or by a circuit of size n log n. Many people believe this should be tight, but we just don't know how to prove this now. There are many shifts and permutations of n bits that are believed to require superlinear circuits. Perhaps all NP-hard problems require superpolynomial, at least superlinear circuits. So we have many candidates who just don't have a tool to prove superlinear circuit law. Okay, but in the 70s, William designed a nice framework which we still believe can lead to superlinear circuit law. He said that if you have a linear size circuit, that you can also compute the same function by the following depth 2 circuit. You start with n inputs, you preprocess them. Again, you have unbounded computational power here. Preprocess them in the only epsilon n bits. And then I would like to say that you can compute every output by looking only at a few memory cells. But that would be too much because here, unlike data structures, in the preprocessing stage, you lose information from the input. You go from n bits to epsilon n bits. So you lose some information. I have to allow outputs to look at the inputs as well. Luckily, I went through that if there is a linear size circuit, then there exists a depth 2 circuit where every output looks only at a few memory cells and a few inputs. So if you can find a function that cannot be computed by this thing, you get a super linear circuit law. Okay, so here's what efficient data structure looks like, and here's what a small circuit looks like. Efficient data structure, here you preprocess n inputs into, say, 10 n memory cells, and every output looks only at a few memory cells. Small circuit, you preprocess n inputs into epsilon n bits, and every output looks at a few memory cells and a few inputs. We would like to say that these two pictures are very similar, and if you prove one lower bound, you get the other lower bound, and we don't know. Yet, we recently showed that actually for linear problems and linear data structures and linear circuits, these two pictures are equivalent. If you get the lower bound for data structures, you get a new lower bound for circuits and the other way around. And linear problems, or linear data structures or linear circuits is not a big restriction. In fact, many of our candidate have problems are linear. Polynomial evaluation, matrix vector multiplication, range housing, and partial sums. Look at many candidates of functions which are linear. So this doesn't seem like a big restriction. And in general, linear problem is just defined, by matrix. Then given an input vector, your output is this matrix times the vector. That's the definition of linear problem. Let me give you an idea. Does the result make sense? If you have any questions? Let me give you some idea how we could prove such an equivalence. So here's what a linear problem is. Given a vector x, output matrix n times x. Then let's look at linear data structure. So a linear data structure takes input, preprocesses it by some linear operator in a bunch of memory cells, and then every output is again a linear combination of memory cells. In other words, I can say that a linear data structure just multiplies two matrices. One matrix encodes the dependence of memory cells on the inputs, and the other matrix encodes the dependence of every output on the memory cells. That's all what it does. Computes two linear maps sequentially. So data structure computes matrix n if it can be written as A times B, where A is a matrix responsible for these connections and B is a matrix responsible for this connections. And recall that efficient data structure, in an efficient data structure, every output reads only a few memory cells. So this matrix A is sparse. Every row looks only at a few positions in the data structure. Also know that like a typical data structure problem has very large number of outputs, like n squared, n to the 10 or something. So this is a matrix of size, say, n to the 10 by n. And this is a small matrix. S, like the number of memory cells you use is, I don't know, n log n and polylog n. So this is n to the 10 by n, and this is like n polylog n by n. So this matrix is actually small. So a linear program admits an efficient data structure if and only if it can be written as a sparse times small matrix. Okay. On the other hand, let's look at linear circuits. So we already.
Why is the A necessarily sparse?
A is a matrix where each row corresponds to an output. Each column corresponds to a memory cell. And it encodes the dependence of outputs on memory cells. In an efficient data structure, every output looks only at a few T memory cells. So every row has only a few T non-zero entries. Okay, now let's check out linear circuits. We already know that a small circuit, linear size circuit, can be written in the following way. So again, I can say that my matrix n can be written as a matrix A that gives me dependence of outputs and inputs, plus a product of two matrices that encode the dependence of outputs on data structure and data structure on the inputs. And again, I know that two of these matrices are sparse. The matrices that encode the dependence of outputs on memory cells and inputs. In particular, I can say that my matrix M can be written as a sparse plus low rank matrix. This matrix has low rank because it's a product of two small matrices. One of their dimensions is epsilon n. So their rank is at most epsilon n. So if my problem cannot be computed by small circuits, it's called a rigid matrix, then it cannot be written as a sum of sparse and low rank matrices. Okay? So what do we have now? A small circuit or non-rigid matrix means the matrix can be written as a sparse plus low rank, small or efficient data structure means the matrix can be written as a product of sparse and small. So all what we're doing in this work, we prove a connection between these two representations of a matrix. We say that if a matrix can be represented in this way, we can find another related matrix that can be represented in this way and the other way. Yeah, so this lets us conclude that any improvement on the known data structure lower bounds would imply a new data structure. Any improvement on the known data structure lower bounds would imply a new circuit lower bound, and any new circuit lower bound would imply a new data structure lower bound. They're in fact equivalent, and for every settings of S and T, space and time, the best data structure lower bounds exactly correspond to the best known circuit bound.
So just a very quick clarification. Can
Yeah.
you just repeat what you said about what is a linear data structure precisely?
Yeah, so linear data structure, for example, we can define it as follows. I mean, that's usually defined as follows. Every element in the data structure linearly depends on the inputs.
Okay.
Every element in the outputs linearly depends on the elements and the linear data structure. In fact, you can drop any of these two restrictions, but not both. If you drop any of them two, of these two restrictions, you will get the same class of data structure.
Okay. And the reason why you're okay with this is because there are still hard problems.
Yeah, there are still hard problems. Again, a random problem is hard. Again, we don't know how to prove any level on that.
How powerful is this kind of data structure?
So,
How powerful is this kind of data structure?
I mean, they compute all linear problems. Yeah, it's a complete model for linear problems. Same with a linear circuit. They can compute any linear function by counting a random problem is hard. And the best lower bounds for linear data structures or linear circuits are exactly the same as the best lower bounds for nonlinear data structures.
I mean, in terms of the trade-off.
Oh, like what's the complexity of a random one? Okay.
Wait, let me ask the question, same question. So like, could it be the case that like is there an example of a linear function which has a very efficient non-linear data structure, but not necessarily an efficient linear data structure?
So that's a big open question, and in fact, there is a conjecture from 2010 by Yuta and Schneider that says that if you consider a linear problem, then both in circuits and data structure regimes, optimal construction for it is linear. They do not exactly specify what they mean by optimal, like after a constant factor or something. But yeah, we do not know separation between linear and nonlinear constructions, circuits, or data structures for linear problems. In an upcoming work together with Yang Kun Ko, we proved a very special case of this conjecture. We proved that for data structures that use little space, the conjecture is true. More questions?
The last part, right? That's where you have the A part.
Where can I say?
This one, right? Is there a construction for this? I mean, is there a algorithm which will give you this?
Yes. The variance procedure is a very explicit procedure. Yeah, it's based on a result of Erdős Breckman and Sarid from 1966, which is an explicit procedure that takes any circuit, cuts it in a simple deterministic way, and gives you the absolute circuit that completes the same function. Okay, so yeah, this representation of the linear data structures and linear circuits let us actually conclude that these two questions are equivalent. So any improvement on either lower bound would give us better lower bound for the last.
So I have a silly question if you will.
Yeah.
The improvements that we saw for the crypto case in terms of pre-processing were all on, small improvements, right? They're like going from n squared to n raised to 6 or something like that, right? So, I mean, what does that imply in terms of hardness of all of these problems in general, right? So you're only improving from a quadratic to a linear kind of case, right? So does that really make sense for cryptography?
So you're saying, say, for three sum, our improvement is from n squared to n to the 1.9. Does it really give you anything?
Yeah.
Okay. Yes, because actually for secure cryptography, the lower bound we need is like any polynomial lower bound on S when C is just polylog of n. For cryptographic applications, we don't need this S and C to be exponential.
Okay.
In fact, this n will be exponential in I don't know, the security parameter.
I see.
So we need lower bounds which are much weaker than the upper bounds we can put. We need a lower bound that says for any t which is polylog n, S must be at least n to the 1.1. And we're still very far from proving such lower bounds. In particular, they would imply amazing circuit lower bounds.
The virtual stuff is which is basically dictionary attacks, right? Okay, that's fine. We understand. And that's an efficient dictionary attack.
All right, thank you for your attention. Today we've seen some connections between data structures and cryptography and circuits and data structures. Yeah, please let me know if you have more questions.
Time for questions.
Let me ask an obvious obvious question given your picture there. You like combined 3 of the 4 hardness
Yeah.
topics. Is there any hope for connection to the 4th?
Oh, there are known connections.
Okay.
Yeah, there are known connections between crypto and learning and circuits. They're amazing, but yeah, we didn't cover them in this talk. For example, I mean, Golovnev is a classical example of connection between cryptography and learning. The Golovnev algorithm gives you a way to construct pseudo-random generators in cryptography, but it also gives you a way to learn structured classes of functions in the PAC model. Connection between one of the probably the first connection between learning and circuit complexity was the work of Portman and Lyons, which said that if you have an efficient deterministic sub-exponential deterministic factoring algorithm for a class of circuits, you get a super polynomial lower bounds for this class of circuits in an E, I believe. But there were several improvements on the platform. Yes.
So, it's well known that a multiplier cannot be encoded as a DD efficiency.
Right. But we don't know
connection
to
with
generalize it to
and-
more
and-
powerful models of computation. Yeah.
So this circuit for the multiplier is quite different.
Yeah, I mean the best constructions they take time and log n and they're quite different, but we don't know how to prove our bounds yet. The model is stronger, we don't know how to prove our bounds.
So why do you think this multiplication is a good candidate for proving lower bounds and you cannot prove lower bounds for much harder problems?
So actually, when William designed this framework, his candidates for hard functions were just shift functions. Those functions that have, say, n plus log n inputs and outputs. This log n inputs tell you a number from 1 to n, and you just need to shift input, like say, perform a cyclic shift by this number. So outputs will be just shifted inputs by this number, and that was conjectured to be a hard problem even in his model by many people like Peter and Van in the 70s. And this is the essential part of integer multiplication. This problem starts even only if integer multiplication starts. And so people still couldn't figure it out, and so people can still believe that integer multiplication is
It was interesting that like your list of problems, you chose problems with non-trivial algorithms, right? And like multiplication has like highly non-trivial algorithms to get n log n.
right,
Like-
with T, yeah.
Yeah.
Yeah, but I mean, those are problems where we believe we already get tight upper bounds, essentially.
Yeah.
So it just remains to prove a lower bound.
Just.
Yeah,
Can you say something about the pre-processing part? So suppose there is a bound on the pre-processing in case of cryptography with pre-processing, then does it imply some pre-process, some bound on the pre-processing in case of data structures? Why
Yeah, yeah,
Google
yeah.
has that power, but it is very limited. And
yeah. So, yeah, no, the connection goes two ways. Essentially, if you have an immunization procedure, if given a function which was secure against, okay, if given a random oracle, we can construct a function which is secure against attacks with preprocessing, then from this, from your definition of G, I will extract a data structure program for you to can prove a strong data structure lower bound. Yeah, the lower bound will be essentially proportional to the amount of preprocessing you're securing. Yeah.
Okay, more questions? Okay, if there are no more questions, let's thank Sasha again. This week, we are going to have another CS colloquium on Friday. So you are welcome to come by on Friday at 3:30. It will be slightly different time. We conclude the seminar for today.